Hello, welcome you all. So today we'll study what is moment of inertia, what really the moment of inertia is. So let me write down the name of the topic, moment of inertia. It's a very very important topic of rigid body dynamics. So what is moment of inertia? So we have already familiar with the word inertia. So it's a we study Newton's laws, and we study in inertia that mass has some inertia, so it will it will uh, it will like it if it is if it is moving, so it will keep on moving until unless there is no external forces applied and things like that. So moment of inertia is same analogy from that Newton's laws, but it is for rotation of some particle about some axis. So let me draw some axis. Say it is our axis, and I have mass r. This mass m. This is our mass m from the distance r, and this is our axis. So I am rotating. I'm rotating this mass about this axis. Okay. So if we have to apply some torque or force to to rotate it say it initially at rest, so we have to apply some torque or force uh, to 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 make it rotate. And say if it is rotating, so to stop it we have to apply some reverse torque in the opposite direction, so that we can make it stop. So so but they but you see here, if you want to, if mass if our mass is over here and I am applying it force to this mass, so it will be easy for me to rotate it. It will be easy for me to rotate it with comparison to here, over here. If I want to apply force over here, so it will, I need some more 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 force. No, let me again write my word wisely. So I need less force over here, less force over here, but the but torque will be generated more for the same force. I don't know how many torque is r cross f. So same force, if you will apply over here, the force you will apply over here, and the same force apply over here. So more torque will be generated over here. Uh, mm, more torque, more torque, less torque. So so it it is our moment of inertia, and the definition for moment of inertia goes like this. It is I m r square. Let me use small r because I have written small r over there. So mr square for this mass m. And so this is our moment of inertia. Now in real world we don't have any, we have particles, which we do generally do not deal in mechanics. We do not deal with the particle. It is some extended object. Always it is some extended object, some random object rotating about some excess, and it will have some point point masses. We can assume that it is made of these point masses, rigid rigid with this with respect to each other. Okay, and each one of them will have some distances. Say it is having distance r1, r2, r3, r4, and so on, r5, r6. So this is it. And writing down the sum of all these masses, particle point masses, and their distances, this will give us total moment of inertia of this body, this object. So it's a very general body, but we can we can analyze some familiar bodies, more symmetric bodies. We can calculate their moment of inertia. What is their moment of inertia? So let me go directly to the a very familiar object, that is a ring. It's a ring. We have this ring over here, and it is given mass m, radius r. This is radius r. Say this is some angle theta with respect to x-axis y. We will have a perpendicular axis, z-axis, going from this the center of the ring. So we can always rotate this ring with respect to the z-axis. This is our z-axis, and this is our ring. So now it look more like a symmetric thing, omega. So we are rotating this ring. So what is the inertia? We have to calculate. This is radius r. This is theta angle. So we can assume that there is a dm mass. It made of dm masses. The whole ring is made of dm masses. So let him, and uh, writing the definition of moment of inertia, that is dm r square. This is just the definition. For this point mass, I will be having this moment of inertia di. This element mass, I will be having this moment of inertia. Now using this, I want to calculate the moment of inertia of this whole ring. So there is a more mathematical way, but let me go into some more vague sense, the what is the moment of inertia. So so let me calculate using that way what will be the moment of inertia of this ring. So distance is constant for all of these masses dm. It is also at r distance. 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 Okay. So r is not changing for all of these masses. So I can write again. So let me say this is di1, di2, dm r square, and all the way up to my last. So this way I have calculated the all moment of inertia. Now let me add all of them. So that will give me di1, di2, and this will give me dm, 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 and r square. These are very small masses, so the summation will become in integration. Here it also become an integration, and dm, thus total dm already given mass, thus the integration of dm will give us this mass capital M that is given already. So mr square and di will give us I. So this way we have got the moment of inertia of this ring. And let me give you one more analogy in this, so you get the grasp of what is the moment of inertia is. Say I was having initially initially I was having this big chunk of this capital M, you see the the total mass of this ring and this brick of mass M is same, and it is at distance r, and if I use the formula it will give me half mr square only. And with the some technique I melted it and created a ring of this mass. So whole mass get distributed around the periphery of the ring over here, so it becomes ring. But the distance of the mass, that never changed, that remained constant r. So so that's why the moment of inertia for this brick and the ring is same. Got it? So this is the moment of inertia of this ring. Let me go in more mathematical way. Let me write more mathematical way. Way. This is more mathematical way. So you see, you will get to know why it is more mathematical. It is beautiful, but still mathematical. So again, drawing the figure. This is our ring. This is our xy axis, z axis. Again, dm. So this dm have have arc length of dl. Okay, say dl, and it is projecting a angle d theta over the center. It is a projecting angle of d theta, and in the distance of this mark dm is r. So that's our construction. So moment of inertia for this dm will be dmr square. Same definition I've used. And now I want to calculate the whole mass of this ring, whole mass of this ring, whole moment of inertia of this ring. So I will use integration. So integration di dm r square. Dm will be related to some relation dl, because I have to relate this dm with this r square. Okay, because dm and r square are just two different things, and I've got integration, so somehow I have to relate them. So how to relate them? So so say this ring has the linear mass density of lambda, and that will be equal to capital M divided by 2 pi r. And for and that the the linear, because it is linear, the mass density is same over here, over here, over here. It is all over the same. So so dm is that, so m over 2 pi r will be equal to m over dl, dm over dl, and this will become r d theta. Okay, now dm will be equal to m over 2 pi d theta. And so I got this relation over here. dm is related to m over 2 pi d theta. So d theta, I've got d theta. Okay, so let me write down this expression. Integration di m over 2 pi m over 2 pi d theta r square. Limits will be from 0 to 2 pi because this is the ring. So angle here it is projecting, it is 0. Then here it will some theta. Here it will be 180, 270, and again 360. And I'm using radian. So m over 2 pi 2 d theta will become theta. Limits 0 to 2 pi. M and r square will remain intact. So m r square 2 pi 2 pi 2 pi 2 pi will cancel out, and again we are getting same expression. I is equal to mr square. Okay, so two way we have calculated this moment of inertia. Now let me give you a very interesting insight, more interesting insight. You see, let me again draw this diagram. Again it is same diagram, but this time I am giving you mass, radius, and this this linear mass density, and this time it is not constant, it is changing with this theta. Theta is defined with respect to x. This is z axis. Okay, this is r, and there will be some dm d. This is d theta, this is dm, having some arc length dl. Okay, and let's say lambda is lambda naught cos theta. So for theta is equal to 0, lambda will be lambda naught. 90, it will be 0. Theta is equal to 180. Now you see I am getting -1. And now what is the sense of -1? It is not a very realistic problem. You say it is mathematically it is correct, but in reality we don't have negative masses. So let me put over a square over here, cos square theta. So it will fix the things. It will give +1. The function has really changed, but the problem is more realistic now. Theta 270, it is give us 0. Theta 360, lambda is lambda naught. Okay, again same thing. Di dm r square. Dm is again lambda dl r square. Lambda is already given, that is lambda naught. Lambda naught cos square theta dl r square. Dl is r d theta. So lambda naught cos square theta r d theta r square. Constant terms will come out from the integrations. Again limit 0 to 2 pi cos square d theta. So how to solve this cos square d theta integration? So we have got this trigonometric identity cos square theta 1 plus cos 2 theta divided by 2. So we can use this trigonometric identity to simplify this integration. 0 to 2 pi plus cos 2 theta divided by 2 d theta. 1 by 2 lambda naught r cube. 1 will become theta and cos 2 theta will become sin 2 theta. 0 to 2 pi and sin 2 theta will give one more. Putting these limits, 1 by 2 lambda naught r cube 2 pi, 2 to cancel out, lambda naught r cube pi. So this is our moment of inertia. So there is lambda naught. So how to fix this lambda naught? Because I have to show you some form of mass r square, something like this, and this looks nothing like this. So I have to somehow convert this lambda naught to m. Okay, m and r. So how to correct it? It is correct, but how to write this mr square type form? So I know my dm, total sum of dm's, and dm is our lambda dl, lambda r d theta. Lambda is given lambda naught cos square theta r d theta dm. So lambda naught cos square theta r d theta and lambda naught r cos square theta d theta. 0 to 2 pi. Again, solving this integration, we will get pi. So lambda naught r pi is equal to m, lambda naught m over pi r. We have got this expression. Now I is equal to putting this putting let me show you, putting this over here. So I will become m by pi r cube pi. So isn't it amazing that finally we have got this expression I mr square, and it might have come different, it might have, but we are getting the same expression I is equal to mr square. And why it is happening? You see, I have already given you insight about it, why it is happening. See, even though that the mass density is changing, it is biggest over here, then little less over here, 0 over here, then it is again increasing over here, again biggest over here, decreasing, hollow, then again increasing, and the pattern repeats. But the thing is, the distance of the mass is dm. That doesn't really change, and until that doesn't change, we can use same this this thing. We can, I already, with without even going in more mathematical aspects, we can directly use this dm, and I know dm are different, dm will be different, but the total sum will be m, and distance is constant, so integration doesn't really depend on that, and sum of dm will give me capital M. So for linear, for the constant linear density, the dm, all the dm's were same, but for variable linear density, the dm will be different. Every dm will be different, but the total sum of them will be capital M. So that's why I'm getting this mr square. Okay, And if you use that brick analogy I given you, we can see using that also. So I was getting I m r square for this mass. Okay, and I mold this mass in such a way that my mass density is highest over here, zero over here, and it decreases over here, increases over here, decreases over here, then again increases over here. So so nothing really changes. I is equal to mr square. That is same na. So that's why we are getting this I is equal to mr square expression. There is this one disk example also. Disk, you know, disk. It is filled with the mass. It is it is not having mass only at periphery. It is having mass over here also. Okay, and we can calculate the moment of inertia of this also. And let me show you how quickly that how we can calculate it. So this is my disk. So a we can assume a ring. We can assume a ring of some width of some dx width. This is my ring of some small width, and the width of this is dx. This is say width of the ring is dr, and this is r, and the mass uh, this ring element is having with respect to this disk is small dm. So I know already the moment of inertia for the ring. So di dm small r square. This will be my this ring this this ring element moment of inertia, and we can have some smaller ring. We can assume this this disk to be made of these smaller rings and some bigger rings, and summing up them will give us this moment of inertia of this disk. Okay, so let me calculate them using that analogy. Let me calculate the moment of inertia. So integrate di dm r square. Okay, and how to relate this dm with this r? The main goal is this, and if we are successful to find this relationship, our integration will be solved and we will get this I. So our purpose is just to find this dm and r, small r relationship, and our disk radius is capital R. It is capital R. Okay, so so dm, say whole mass of this Disk is capital M, dimension is capital R. So M by R, the area mass density, areal mass density. Okay, that is defined by the sigma, and M by pi R square. The whole mass is distributed in the area of this disk. So that is our sigma, and sigma, that sigma will be equal, this M pi R square sigma, it will be equal to dm and the area of this ring. And now you would say the area of the ring. What is the meaning of that? Yes, there is some area of this ring. That is the the, the circumference of this elemental ring, and multiplied this dr. So circumference is 2 pi r and multiplied this dr. You say this is our ring, elemental ring, and if I cut cut it from here with the scissor, so we can unroll it like this. So this is 2 pi r, this length is 2 pi r, and this is dr. So width into height, it will give us this area of this elemental ring. So dm is m pi r square 2 pi r dr. Pi to pi cancel, m by r square r dr dm. So 2 is left over there also. So this is the dm expression, and substituting this dm expression over there, 2m r square r dr r square. These terms are constant, so they will come out of integration. Limit be from 0 to r, because we are starting from the center and we are going up to periphery of this thing. So 0 and r. So that's why 0 to r cube dr. This integration is very simple. 2m r square r to the power 4 divided by 4, 0 to r, 2m r square r to the power 4 divided by 4. Half mr square. So I disk is half mr square. Now you see, many times students get confused that what, why we are getting this half mr square. I was getting mr square over there and half over here, while it is looking like that that the disk has more mass, and why the less moment of inertia. So the reason is quite simple. You see, we forget the basic definition very often, but see, basic definition is that I multiplied by mr square. And you see, the in the ring, this is my ring, this is my disk. In the ring, the mass is distributed over here only at the distance r, and the masses of both the objects are same. It is of capital M and it is also capital M. Ring is not light or heavy. If you will measure their mass, it will come out to be same. So the only thing that is different is their mass distribution. The mass distribution in the ring is only at periphery, and here it is on in even in the area also. So so you see here DM masses, they are at less distance, and here the DM masses, all of them are capital R distance. So some DM masses, still there are DM masses at capital R distance, but 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 there are masses or DM masses also that are not as capital R distance. So there is a distribution of, so that's why we are getting this half mr square. Okay, so that's all for today. I think whatever I have explained you have got it. That's it. That's all. Thank you. Thank you.